last lecture of our previous lecture, we had started with effects from relativistic consideration. The Schrodinger equation is a non-relativistic equation. We started with the relativistic mass energy relation, from which we derived the relativistic equation, and in fact we wrote the relativistic Schrodinger equation, wrote it in a form H psi is equal to H naught plus H prime psi, that is the total Hamiltonian is written as the sum of H naught plus H prime psi is equal to E prime psi, where H naught is the non-relativistic Hamiltonian, that is this is equal to minus H cross square by 2 m del square plus V of r. And for the hydrogen atom problem, I know the solution of the eigenvalues of the eigenvalue equation for H naught, and my H prime was equal to minus E prime minus V of r by 2 m c square, and the numerator was square. So, this was the Hamiltonian, and this is the, we will take H prime as a perturbation. We will take H prime as a perturbation as you and use the perturbation theory to calculate the effect of the term H prime on the energy eigenvalues. Now, for H naught, we know the eigenvalue equation, we know the solution of the eigenvalue equation. In fact, H naught psi n L m is equal to E sub n psi n L m, where psi n L m is a function of r, theta and phi, and these wave functions are given by psi n L m functions are r n L, a function of r, times the spherical harmonics y L m theta phi. Now, therefore, we want to use the time independent perturbation theory. This is my perturbation. So, we want to calculate this matrix element n L prime m prime for the same value of n. You see, different values of n will have different energy, as we all know that E n is equal to minus E 1 plus E 1 by n square, and for the hydrogen atom E 1 is about minus 13.6 electron volts. So, let me first calculate the matrix element H prime n L m. So, this is actually the integral, the triple integral psi n L prime m prime star H prime psi n L m r theta phi, this is as a function of r theta phi multiplied by d tau, and that d tau is equal to, this is the volume element, and we will use d tau is equal to r square dr sin theta d theta d phi. Now, in this we must see that H prime is a function of r only, and so we can write this integral as a product of two terms. Since this is a function of r only, we can take the r side. So, let me write it from here. The first integral will be 0 to infinity r n L prime of r star, but these are all real function, H prime r NL R square dr multiplied by integral y L prime m prime star y L m sin theta d theta d phi. So, that there is a simpler way to write this. So, this is d omega, where d omega is sin theta d theta d phi. This we abbreviate as. Now, they form orthonormal functions. So, this is equal to delta L L prime delta M M prime. So, since H prime depends only on r coordinate, so this matrix element becomes equal to 0 to infinity. L must be equal to L prime, otherwise it is 0. So, this is H prime r n L of r whole square r square dr multiplied by delta L L prime delta M M prime. So, you see what I am trying to say is that I consider, let us suppose, the n equal to 2 state, and as we had discussed in the Stark effect problem, this is 4-fold degenerate. So, among the degenerate states, our wave functions are such that any element like h prime 1 2, h prime 2 1, h prime 3 1 and so on will be 0. So, we already have a representation in which h prime is diagonal, and so therefore, the diagonal elements will be the perturbation. So, therefore, due to relativity effects, due to the delta E, due to relativistic effects, will be just the diagonal terms when L is equal to L prime and M is equal to N pi. So, this will be H prime is so this will be just 0 to infinity H prime r n L square of r square dr. This will be the perturbation, and H prime we know that this is equal to minus E prime minus V of r whole square by 2 m c square. So, we can write this down, that this is equal to minus 1 over 2 m c square E prime square, and V of r is equal to minus Z E square by r. So, this becomes E prime plus Z E square by r. So, this will be minus 2 E prime. So, this will become plus 2 E prime Z E square by r plus Z square E 4 by r square. So, therefore, since these are normalized functions, that is what I mean by normalized function is integral of this quantity from 0 to infinity is 1. So, therefore, the integral, if I carry out the integration, so this becomes equal to, let me shift it to the right. So, that this will become is equal to so, therefore, delta E relativistic due to relativistic effects becomes equal to minus 2 m c square E prime square plus 2 E prime Z E square expectation value of 1 over r plus Z square E 4 expectation value of 1 over r square, where 1 over r to the power of p is equal to 0 to infinity 1 over r to the power of p r n l square of r square dr. Now, it so happens that some time back I had given you the formulae for obtaining RNL of R, the radial part of the hydrogen atom wave functions, and in fact using each one of them I can calculate this integral, evaluate this integral. The integration is really very simple. However, there are general formulae which are available, and I will just give you the result. The expectation value of 1 over r is 1 over n square z by a0, where a0 is the Bohr radius. So, a0 is equal to h cross square by me square and has a value of about half of an angstrom, and 1 over r square is the expectation value of 1 over r square, and that is given by this expression, and similarly for 1 over r cubed. These are given at many places, including the formulae are given in this book, and there is a book by Maggiari, Problems in Quantum Mechanics, and in which these relations are very carefully problems in quantum mechanics. So, you can see them if you are interested in finding out the derivation of these formulae. So, you have here these formulae. So, if you substitute it here and carry out a very straightforward algebra, then you will obtain the following expression for the. So, we write it in wave number units. So, in wave number units, delta t will be equal to delta E relativistic. This is the relativist expression of the change in the energy divided by hc. Delta t is in wave number units, and if you do that, you will find that this is equal to minus alpha square z4 by n to the power of 4 multiplied by r is the Rydberg constant, and multiplied by n divided by L plus half minus 3 by 4. So, alpha we know, alpha is equal to the fine structure constant, which is in CGS units, it is E square by h cross c, which has a value of 1 over 137. For the hydrogen atom, Z is equal to 1, and n in the denominator is the total quantum number, and the r is the Rydberg, which for hydrogen atom is 109678 centimeter inverse. So, we know all the parameters, and for example, for the 2p state, p is equal to p means L is equal to 1, and for the 2s state L is equal to 0. So, we find that for L equal to 1 and L equal to 0, the value of this expression is slightly different, and we obtain a splitting of the level. This splitting is known as due to relativistic effects, and the final result is for the 2p state and similarly for the other state. So, this is the relativity correction. So, you have here n equal to 2 state, the splitting, the change is 0.213 centimeter inverse. These are very, very small, and the for n equal to 0, it is 1.1870. So, due to the relativity effects, the degeneracy is partially removed. The degeneracy is only partially removed, because n equal to 2 state is 4-fold degenerate state, but it splits into 2 states. L equal to 0 state is non-degenerate, L is equal to 0 state is non-degenerate, and L equal to 1 state is 3-fold degenerate, because the m values takes -1, 0 and +1. So, because of the relativity effects, the degeneracy is partially lifted. But when you compare this splitting, which is known as the fine structure splitting. So, we find that the experiment does not agree with the theory, because of the same order of magnitude is what is there is the spin orbit interaction. Now, so we have taken the relativity effect. We will next consider the effect due to spin orbit interaction. What is it physically? Now, you see, let us consider the simplest of the atom, the hydrogen atom. Now, in the hydrogen atom, in the Bohr model, the electron rotated around the proton. So, therefore, if I am sitting on the electron, then the proton is rotating around me. If I am sitting on the electron, then with respect to me the proton is rotating. So, it is a circulating current. So, it produces a magnetic field. Because of the circulating current, we have a magnetic field at the electron, and since electron has a spin angular momentum, or rather electron has a magnetic moment, it behaves like a tiny magnet of magnetic moment mu. So, that magnetic moment interacts with the magnetic field of the due to the orbital motion, and so we have an interaction energy which is the mu dot h term, which is known as the spin orbit interaction. Now before so therefore, if so this was the final formula for the which I would request using these expressions. Using these expressions, I would request all of you to derive the expression for delta t relativistic and show the explicit splitting of the n equal to 2 state, which will split into 2 state. One will be L equal to 0, the S state, and the other will be L equal to 1 state. We next consider, as I just now mentioned, the spin orbit interaction. Now, because of that, we have a Hamiltonian, we have a perturbation term which is proportional to L dot S. In fact, the perturbation term is which comes out automatically from the Dirac equation 2 m square c square 1 over r cubed L dot S vector. So, where this is the orbital angular momentum vector and S vector is the spin angular momentum vector. So, we write this as that we multiply this by 2 and divide by 2, and we write 2 L dot S. We define the vector, the total angular momentum vector is equal to L plus S. So, we had considered the addition of angular momentum. So, 2 L dot S will be Z E square by 4 m square c square 1 over r cubed. 2 L dot S will be j square minus L square minus S square. Now, our perturbation is therefore proportional to j square minus L square minus S square. So, I must consider the functions which are simultaneous eigenfunctions of j square, L square and S square. So, these are the 5 functions that we had discussed. So, here for example, L the eigenvalues of L square is equal to L into L plus 1, eigenvalues of L square is L into L plus 1 h cross square, and S is half. So, the eigenvalues of S square is equal to 3 by 4, half into half plus 1 h cross square. So, therefore, the total angular momentum value J can be either L plus half or L minus half. So, I must choose to calculate the effect of the perturbation. I must choose the 5 functions for which J will be either L plus half or L minus half, and then J square L and then half, j square, L square and S square. So, those are the eigenfunctions that we must choose, and if we carry out this integration, calculate the matrix element, that is phi j equal to L plus half, L half and m j, these are the wave functions, H prime and the same wave functions phi j L half m j. Now, you must understand that the values of j for a given value of a, values of j will be either L plus half or L minus half, of only for L equal to 1, 2, 3. For L equal to 0, it will be just half. The eigenvalues of j square will be j into j plus 1 h cross square. The eigenvalues of L square will be L into L plus 1 h cross square, and eigenvalues of S square will be 3 by 4 h cross square. So, we use these wave functions. We can explicitly write down the form of the wave functions, as we will do slightly later, but we do not have to do that. As long as we take these wave functions, we know that this will be equal to. So, therefore, the perturbation will be equal to the delta E, the change in the energy because of the spin orbit interaction. This will be, this factor is a constant, z E square by 4 m square c square, the expectation value of 1 over r cubed multiplied by j into j plus 1 minus L into L plus 1 minus 3 by 4 h cross square. Okay. So, we have already told you what is the value of 1 over r cubed, the expectation value of 1 over r cubed, that is equal to 1 over L n cubed, this rest to the power. So, we will use this, we will substitute this here, and we will use this for j is equal to L plus half and j is equal to L minus half, and the calculation is really very simple. For example, for j is equal to L plus half, we have this expression is equal to L plus half into L plus 3 by 2 minus L into L plus 1 minus 3 by 4. So, this is equal to L square plus half plus 3 by 2 is 2 L plus 3 by 4 minus L square minus L minus 3 by 4. So, L square cancels out, this cancels out. So, this becomes just L. So, I divide L comes there and one of these L get out, and so we will get an expression for delta A. Similarly, for j is equal to L minus half, j is equal to L minus half, this becomes L minus half plus 1, that is L plus half minus L square minus L minus 3 by 4. So, this becomes L square minus 1 by 4, minus 1 by 4 is minus 1 by 4 minus L square minus L minus 3 by 4. So, L square cancels out. So, this will become minus L minus 1. So, minus brackets L plus 1. So, you will have a minus sign there. Here, as you can see, this is a plus sign here, and the other will be a minus sign here. And the rest of the calculations are very simple, and in fact, if you work this out, then you will get the following simple expressions, that delta E, delta E due to spin orbit, it becomes Z4 alpha 4 mc square by 2 n cubed L plus 1 into 2 L plus 1 for j is equal to L plus half, and similarly in another expression for L plus L minus half. If you add this, so the second expression, let me write it down, this is plus here, it is a positive, and the next as I mentioned, for j equal to L minus half, this becomes z to the power of 4 alpha to the power of 4 mc square divided by 2 n cubed L into 2 L plus 1. If you add to this the expression for the relativistic correction and then use wave number units, the final result becomes delta T, the fine structure. Fine structure is the sum of the relativity effect plus the spin orbit interaction, relativity effect plus the spin orbit interaction. So, this comes out to be very simple. You can put it, combine into one formula, alpha square z 4 to the power divided by n to the power of 4, r is the Rydberg constant, n by j plus half minus 3 by 4. Z is equal to 1 for hydrogen, alpha is 1 over 137, and the Rydberg constant value I have taken. So, for hydrogen this comes out to be a very simple number, 5.845 for hydrogen. This divided by n to the power of 4, n by j plus half. It does not really depend on the L value, it depends only on the, this is fine structure is relativity correction plus the spin orbit correction. So, if I now I had here, for example, the relativity correction is given by this, and this is my spin orbit correction. So, on the I superpose this on the relativity correction, I superpose the spin orbit correction, and therefore, this 2 doublet p half, this 2 represents the total quantum number, doublet means s is equal to half, and these are the j values, j is equal to 3 by 2 and j is equal to half, and this is doublet s half, both of them have the same energy level. So, both of them, it depends not on the L value, as we see from the last expression. This is the relativity plus spin orbit correction, and so this is the fine structure of the spectral line. This is known as the fine structure. So, what is the fine structure? Fine structure is a combination of relativity effect plus spin orbit interaction. The hyperfine structure, which is even a smaller splitting, is due to the interaction, for example, in the simplest of the atom, hydrogen atom case, the electron has a magnetic moment, the proton has a magnetic moment. The two magnetic moments interact to produce an interaction term, which results in a further splitting of the spectral lines, and that splitting is known as the hyperfine structure. That splitting is extremely small. So, you can see here this splitting depends only on the total quantum number and not on the L values. So, let me show you some of the calculations that I have. I mean, these are very simple calculations, and I would request all of you to do that. These are all for the hydrogen atom, n is equal to 1. As you know, for n is equal to 1, L is equal to 0, and so therefore, J will be only half. So, you have 1, that is the total quantum number, doublet because S is equal to half, S half. For n is equal to 2, just what I had shown, the fine structure is, this is 0.091 centimeter inverse, and therefore, this is the 2 doublet P 3 by 2 and P half and S half. The splitting depends only on the J value. Similarly, for the n equal to 3 state, let me write it down, L can be 2, L can be 1 and L can be 0. So, when L is 2, J can be either 5 by 2 or 3 by 2. These are the D 5 by 2 and D 3 by 2. When L is equal to 1, so this will be 1 plus half, that is 3 by 2 and half. This is P 3 by 2 and P half. When L is equal to 0, then it is only half. So, these are the, so n equal to 3 level splits into 3 levels. Once again, the degeneracy is only partially lifted. And when you have n is equal to 4, then L can take 3, 2, 1, 0, and you will have the F states. F states corresponds to L is equal to 3. So, this can be either 7 by 2 or 5 by 2. So, it is here 7 by 2, 5 by 2, and then D 5 by 2, D 3 by 2, P 3 by 2, P half, etc. The splitting, the value of the splitting depends only on the J value and does not depend on the L value. Okay. And when there is a transition from one of the lines to the other, then you have obtained the fine structure splitting of this spectral line, and that is what we have shown here. The Balmer series, one of the lines of the Balmer series which you have all read in your high school, is from the n equal to 3 to n equal to 2 transition. And let us consider the n equal to 3 to n equal to 2's transition corresponds to the H alpha line of the Balmer series, and this has a wavelength of about 6565 angstrom in the visible region. So, the n equal to 3 level splits into 3, the n equal to 2 level splits into 2, and when the transition takes place, let us suppose from 3 doublet S half from this level to 2 doublet P 3 by 2. So, from this to this, the shift is 0.071, and similarly from other levels to the other level, there is a small change in the energy. I would request all of you to calculate this shift and show that it results in 5 spectral lines. That is, this line, if you use under a very careful spectroscope, a spectroscope with a very high resolution, then the n equal to 3 n equal to 3 to n equal to 2, this is the H alpha line of the Balmer series, is not really a single line. It consists of 5 lines. This splitting of one line into several lines is known as the fine structure splitting, of the spectral lines. So, I have given you the very important formula. This is of course for single electrons, that delta T fine structure is equal to so much. It depends on the total quantum number. The splitting therefore depends on the total quantum number and also on the J value. It does not depend on the L value, and using this we calculated the splitting of different lines for n equal to 3, n equal to 2 and so on, and we found out the fine structure of the spectral lines. Now, this completes the fine structure. We have taken into account the effects due to relativity and effects due to relativity, and there the perturbation was equal to a function of r only, but then we considered the effect due to spin orbit interaction, and we considered the corresponding perturbation to the energy level resulting into splitting, which depends only on the value of J. Let me tell you that the perturbation term that we had taken was proportional to something like, it was actually Z E square by 2 m c square, 2 m square c square 1 over r cubed L dot s. So, we wrote down this as L dot s. Now, L we know these are operators Lx, Ly, Lz, we had done that. For example, Lz is the minus IH cross delta by del phi, and the eigenfunctions are the spherical hammer. What does this represents? So, for example, this represents L dot S is the Pauli representation of that is, this is what it means, that Lx Sx plus Ly Sy plus Lz Sz. And if you write this down, then this becomes Lx, then Sx is half h cross 0 1 1 0, Ly half h cross 0 minus I 0 plus Lz half h cross 1 0 0 minus 1. So, if you therefore take half h cross outside, so you get Lz here. So, let me write it down carefully. So, this becomes is equal to half h cross outside, and we take a big bracket. So, this term is Lz and minus Lz, and this term is Lx minus ILy, Lx minus ILy, and this is Lx plus ILy. So, this matrix is known as the Pauli representation of the operator L dot S. The subscript P is the Pauli representation. So, similarly, I can write this down for J square, L square and S square. Now, we finally discuss we had discussed the Zeeman splitting for singlet states. We had discussed that if we neglect the effect of the spin, neglect the spin of the electron, then we obtain the splitting, and if we use the selection rule that delta m is equal to plus 1 or minus 1, then we obtain, or 0, then we obtain 3, a level splits up into what are known as a Zeeman triplet, Now, if I look at this state, if I look at the 2 doublet p 3 by 2 state. So, this 2 doublet p 3 by 2 state, L is equal to 1, S is equal to half, and J is equal to 3 by 2. So, therefore, if we now apply the magnetic field, this is known as the weak field Zeeman effect, where we have to take these wave functions, and we will just now show that this will now split up into different mj values, and I will show that in a minute. And 2 doublet p half will split up into 2 levels. So, this corresponds to mj is equal to 3 by 2. This is the j value, j is 3 by 2. So, the z component of the total angular momentum vector Jz, the eigenvalues will be 3 by 2, half, minus half and minus 3 by 2. So, this is known as the Zeeman splitting or anomalous Zeeman effect. Now, let me do it little more carefully. So, we will take the Zeeman effect of say hydrogen like atom or a sodium atom. So, you have the perturbation due to, let me write it down as H double prime, and that is equal to mu b is the Bohr magneton mu b by H cross Lz plus 2Sz. Now, this part is due to the orbital motion, because of the orbital motion as I had explained earlier. it has a magnetic moment which is known as the orbital angular momentum, orbital magnetic moment, and it interacts with the magnetic field B, which is assumed to be in the z direction. And then they, because of the intrinsic spin angular momentum of the electron, it has a magnetic moment, and so therefore that interacts with the magnetic field, resulting in this term. So, what is the corresponding Pauli operator for that? So, you will have Lz plus 2Sz. The Pauli operator will be Lz times the unit matrix plus 2 Sz will be plus half H cross the sigma z matrix, the Pauli z component of this Pauli matrix, that is 1 0 0 minus 1. So, this becomes, this is a unit matrix. So, this will be Lz plus H cross 0 0 Lz minus H cross. Okay. Now, now for this state, we must consider the phi functions, and so let me consider, for example, j is equal to L plus half. So, as I had told you, j can take two values, j plus is equal to L plus half, and j minus is equal to L minus half. Of course, when L is not equal to 0, when L is equal to 1, then it can take 1 plus half is 3 by 2, 1 minus half is half. Now, corresponding to j equal to L plus half, what is the corresponding Pauli wave function? Now, this we had determined using Clebsch-Gordan coefficient. L plus half plus, I would like you to look up the 2 L plus 1 R N L Y L M J minus half and L plus half minus M J. I would like you to look up the chapter on Clebsch-Gordan coefficient, and where we had derived these Pauli wave functions R Y L M J plus half. Please see, there is a comma here, there is a comma here. This is not M j minus half, it is M j minus half. M j can take 3 by 2, half, etc. So, 3 by 2 minus a half will be 1. This in Y L M, M has to be 0 or a positive or a negative integer. So, this is M j minus half and this is M j plus half. Okay. So, therefore, let us suppose this is my phi function. So, let me write it down, H double prime is equal to mu b, b by H cross Lz plus 2. So, this is equal to Lz plus H cross 0 0 Lz minus H cross multiplied by H cross. So, this is multiplied by H cross. So, that H cross, no, that is all right, this is Lz plus H. Now, this operates, so H double prime operates on this phi function. Let us suppose we have phi n comma L j plus M j. Okay. So, this will be H double prime H, this is mu b b by H cross. Please see this, Lz, one just has to carefully do this, 0 0 Lz minus H cross operating on this L plus half plus M j plus divided by 2 L plus 1 R N L y L m j minus half, and then L plus half minus m j by 2 L plus 1 R n L y L m j plus half. This is m j plus half, not j plus half. I am sure all of you understand this. So, if I operate this here, so we will get, please see this, Lz will be mj minus half into h cross plus 1. So, that is mj plus half. I hope I have done it right, and h cross cancels out. So, mu b b, and then this is 0 times this. So, multiplied by this whole wave functions, L plus half plus mj plus 2L plus 1 multiplied by R n L y L mj minus half, and then 0 times this is 0, Lz minus h cross, that is mj plus half h cross minus h cross. So, therefore, this is mj minus a half multiplied by L plus half. If you do not do it yourself, you will never be able to understand. So, I would request all of you to work this out yourself, and you will find so interesting, and you will everything, I am sure. It is just a question of patiently. And then bra phi, the matrix element will be bra phi h double prime phi. So, you take the row coordinate of that, multiply that and carry out the integration, and the final result is very simple. The final result, this is the delta E due to the anomalous Zeeman effect. This comes out to be, I would request all of you to work this out yourself, comes out to be j plus half divided by L plus half mj. So, the splitting is therefore proportional to, and I had that slide somewhere, I hope I can find it, the slide that. So, therefore, j plus half divided by L plus half times mj. So, therefore, let me go once more, let me tell you that here this is the fine structure splitting. So, here you have, for example, 3 doublet d 5 by 2, this is the j value. So, this j value is 5 by 2, the corresponding m value will be 5 by 2, 3 by 2, half, minus 3 by 2, minus 5 by 2. So, you see, so this is the n equal to this is the Zeeman splitting of the of the D1 and D2 lines. Now, the D1 and D2 lines correspond to the 2p state to the ground state 1s. So, this to this leads to D2 level states line, and this level to this level represents the, this level to this level represents the D2 line, this level to this transition from this level to this level represents the D1 line. Now, please see that the j equal to 3 by 2 state splits up into 4 states, 3 by 2, half, this is 3 by 2, this is the z component of the total angular momentum vector, this is half, this is minus half, and this is minus 3 by 2, and the doublet p half state splits up into half and minus half. And the splitting, as I had shown, is it depends on L and also depends on J. So, that if J is equal to 3 by 2, the splitting is large, if J is equal to half, the splitting is small. I hope you understand this. So, for these two states, this is half and this is minus half, and let me consider this. So, for j is equal to 3 by 2 and L is equal to, let us suppose L is equal to 1. So, this term, so j is equal to 3 by 2. So, 3 by 2 plus half is 2 divided by 3 by 2. So, this is 4 by 3 mj, 4 by 3 mj. And what are the possible values of mj? The possible values of mj are 3 by 2, half, minus half, minus 3 by 2. So, this line is 4 by 2 times 3 by 2, 4 by 3 times 3 by 2. So, that is, and this is 4 by 3 times 1 by 2. So, this splitting is 3 times this splitting, and when L becomes equal to 0 or L becomes equal to 1, let us suppose, and j becomes, so L is 1 and j is equal to, let us suppose, half. So, this becomes half plus half is 1 and L is, so 3 by 2. So, this becomes 2 by 3 mj. So, this is half of this. So, you can see this splitting, I have drawn to scale, this splitting is twice of that scale. In this case, you have j is equal to half and L is equal to 0. So, if you have j is equal to half and L is equal to 0, so this will be 1 divided by half. So, this will be 2 times mj. So, you see here the splitting is much more than here, and mj can take half and minus half. So, 2 times 2 mj is 2 into half is 1 and 2 into minus half is minus 1. So, these are the splittings. So, this figure, so what I would request all of you is to use this formula to calculate the transition from the P state to the S state, and so P 3 by 2 and half to S half state, and then this splits up, the P 3 by 2 state splits up into 4 levels and P half state splits up into 2 levels. The doublet S half state leads to 2 levels, and this results in 6 plus 3 plus 3 is 6 plus 4 10 lines, and we had this normal Zeeman effect in which we had neglected the effect of the spin. So, it is applicable to this actually happens for all singlet states. So, singlet D2 state to singlet P1 state, this is a spectrum of cadmium, and you have equally spaced lines proportional to m values, and notice that the splitting here is equal to the splitting here, because this is proportional to the m value. So, therefore, we have developed the time independent perturbation theory. We first considered examples from matrix algebra, then we tried to put forward the care that we should take to deal with degenerate states. When we have degenerate states, then we have more than one wave function, and we must try by intuition to choose those wave functions for which the perturbation H prime is diagonal. So, what I mean by that is that if I have a perturbation which is denoted by H prime, then, and if we have two states u1 and u2 which correspond to a degenerate eigenvalue, I must choose such a linear combination such that H prime 1 2 and H prime 2 1 are 0. If I am successful to do that, then H prime 1 1 and H prime 2 2 are the perturbations, and the corresponding eigenfunctions will be, this level will split up into 2 states, and the wave functions for that, the 0th order wave functions will be u1 and u2. If we are unable to do that, then we choose a linear combination C1 u1 plus C2 u2 and form a set of 2 equations C1 H prime 1 1 minus W plus C2 and so on, from the determinant equal to 0. Find out the roots or values of W by setting the determinant equal to 0, and for each value we will find the ratio C1 plus C2, C1 and C2, C2 by C1. From that we will get the wave functions of the split states. That is, if the perturbation goes to 0, what is the wave function to which it will collapse to? So, in fact, we require these, we also considered the application of the Clebsch-Gordon coefficients by choosing appropriate wave functions, so that the wave functions that we choose are simultaneous eigenfunctions of J square, L square and S square. That is how we discuss the fine structure of spectral lines and then the Zeeman effect of hydrogen like atoms. Thank you.